Hello everyone, and welcome. Exams are just around the corner, so let's power up your revision for electricity and magnetism. We're going to follow the entire journey of electricity, from where it's made all the way to your wall socket. We'll cover all the key ideas you need to score. So, let's get started.
I mean, it sounds like magic, doesn't it? But nope, it's pure science. This one question, this simple idea of a spinning magnet, is actually the secret to how our entire world gets its power. So keep that picture in your head as we dive in.
Okay, first stop, the power station. This is ground zero. This is where it all begins. And we're about to look at a super important principle that is the secret behind pretty much all the electricity we use every single day.
Okay guys, pay attention. This definition is a must-know for your exam. Induced current. The two most important words here that you have to remember are cuts and magnetic field lines. You see, you need movement. If nothing is moving, no field lines are being cut, and you get zero current. Simple as that.
So how can we actually see this in action? Well, in the lab, what we do is we take a coil of wire, we call it a solenoid, and connect it to a galvanometer. Don't worry, that's just a fancy name for a current detector. Now watch this. When we push a magnet into the coil, boom, the needle on the galvanometer moves. We pull it out, it moves the other way. But here's the most important part. If we stop the magnet from moving, look, the needle just goes back to zero. That's the proof. No movement, no current.
So, we've made our electricity. Great! But now what? How do we send it from a power plant, let's say, up in Cameron Highlands, all the way down to your house in KL without losing a ton of energy? Well, that's where this electrical superhighway comes into play. And the heroes of this highway are these things called transformers. First, at the power station, a step-up transformer boosts the voltage up really high. Why? Because at high voltage, electricity can travel very long distances with much less energy loss. It's just more efficient. Then, when it gets near your housing area, a step-down transformer does the opposite. It lowers the voltage to a much safer level for us to use. So, just remember, step up for the long journey, step down for your home.
This slide puts the whole journey together. Let's trace the path step by step. Step 1, the power station makes the electricity. Step 2, the step-up transformer makes the voltage super high. Step 3, this high-voltage power travels across the country through the national grid. Yep, those giant metal towers you see along the highway. Step 4, when it gets close to us, the step-down transformer makes it safe again. And finally, Step 5, it goes to a local substation and gets delivered right to your front door.
All right, the electricity has arrived. You go and plug in your phone charger. But have you ever stopped to think, is the current from the wall the same as the current from a battery? The answer is a big no, and for your exam, you absolutely have to know the difference.
This table here makes it super clear. The power from your wall socket is alternating current, or AC. Its direction is constantly flipping back and forth. But the power from a battery is direct current, or DC. It just flows in one steady direction. If we were to look at them on a CRO, which just draws a picture of the current, AC looks like a nice smooth wave, while DC is just a boring flat line. And that alternating nature of AC is what makes it so easy for transformers to step the voltage up and down.
Okay, listen up. Super important exam tip coming through. So many students get this one wrong. Solar panels, you know the ones you see on rooftops, they produce direct current, DC, just like a battery. So please don't get confused and say it's AC. Remember this one, yeah? It's a very easy mark to get or to lose.
Okay, let's talk about something we all care about, money. Your electricity bill. Every appliance you own has a power rating, and how long you use it for decides how much you have to pay. So let's break down the formulas you need to master.
First up, we have power, which is measured in watts. The formula is really easy. P equals V times I. So power is just voltage multiplied by current. Here in Malaysia, our mains voltage is 240 volts. So if your kettle uses 10 amps of current, its power is just 240 times 10, which is 2400 watts. Easy, right?
Next, we need to find the energy used. This is what TNB actually charges you for. The formula is energy equals power times time. But wait, be very careful here. This is where a lot of students make mistakes. Your units have to be correct. Power must be in kilowatts, and your time must be in hours. So for our 2400 watt kettle, we have to convert that to 2.4 kilowatts first. Then, if you use it for 1 hour, the energy used is 2.4 kilowatt hours. That's 2.4 units on your bill.
And finally, how much does it all cost in ringgit?
Well, you just take the energy you used in kilowatt hours and multiply it by whatever rate TNB is charging per unit. So if the rate is, say, 50 cents per unit, then that 2.4 kilowatt hour for boiling your kettle would cost you 1 ringgit and 20 cents. See? It all connects.
So, we know how electricity is made, how it gets to us, and even how to calculate the bill. But let's take a step back. Where does all this energy come from in the first place? And more importantly, how can we be smarter about the way we use it?
Basically, our energy sources fall into 2 main groups. We have renewable sources. These are the ones that won't run out, like the sun, the wind, and water power. And then you have non-renewable sources, like coal and natural gas. These are finite. Once we use them up, they are gone forever. Understanding this difference is so important for our planet's future.
Now let's talk about efficiency. You see, no appliance is perfect. A lot of the energy we put in gets wasted. Just think about an old light bulb. It gets really hot, right? Well, that heat is actually wasted energy. Only a small bit of the electricity becomes useful light. A modern LED bulb, though, is much more efficient. It produces way more light and wastes very little as heat. So that's what efficiency is all about, getting more useful stuff done with less energy.
And that leads us to how we can all save energy. And it's simpler than you think. First, when you buy any appliance, look for that Energy Star rating. 5 stars is the best you can get. Second, and this is the most obvious one, just switch off your lights and fans when you leave a room. Every little bit helps save you money and, of course, helps the environment too.
And that's our entire journey, from a spinning magnet in a power plant all the way to your monthly bill. So I'll leave you with this final thought. The next time you're at an electrical shop and you see that 5-star sticker on an aircon, think about what it really means now. It's about power, it's about efficiency, and it's about the cost you'll pay over its lifetime. All right, that's all for today. All the best for your exams.